let's see if it started now.
Now it maybe is. It now said it's live streaming. I'll just check.
Is it done? Okay. Can you confirm that?
I don't see it still, but it may start because I got a message that it is live streaming. So it should start. 1 second. Yeah, it started. Good. Done.
Okay.
Yeah.
All right. Thank you very much. Yeah. So apologies for. I can maybe include. Oh yeah, I can see it now.
So can we start?
Oh yes, you can start.
Yeah, so hello everyone. We'll start from where we stopped last time. And what I feel is we have to do a little more of statistics as we proceed, because many a times when we are dealing with astronomy data and we want to make inferences, there is a little bit of confusion as to which test we should use and why a certain test, like when is chi-square is used, when is t-test is used, when is Kolmogorov-Smirnov test is used. So a very brief look at that before we get on to the plotting with Matplotlib and then the Seaborn and so on. So a few words on essential statistics which is used by astronomers. So yeah, so what I'll be briefly covering is what are the foundations of statistical inferences, what are probability distributions, estimation of and hypothesis testing, Bayesian inference, bootstrapping and resampling, model selection, non-parametric methods, and time series and multivariate methods, and some comments on these as we proceed. So why statistics matters in astronomy? We all knew, we have discussed last time too. There's tremendous amount of data available now. So astronomical data are noisy, they're sometimes incomplete and biased. And measurements often include detector noise, selection effects, missing data, there's censored observations, or irregular sampling. And we've seen that there are large surveys which are generating massive data like LSST, Gaia, JWSTs, SKA, and so on, right? So there's tremendous amount of data which is noisy, which can be missing data and so on. And for all this, we require statistics. So statistics methods allow us to estimate parameters. It helps us in this hypothesis testing when we want to, suppose we have two samples of data, you have cluster A and cluster B, and we are looking at certain parameters, like we have a Coma cluster of galaxies and we have Virgo cluster, and we are trying to compare whether the distribution of spirals, lenticulars, irregulars, and ellipticals is it same in both. So when you are comparing, so we set hypotheses, null hypotheses, and alternative hypotheses, which we'll have a brief look, and it helps us test whether these two samples or the sample is indicative of the population or not. And so there are various things. And uncertainty quantifications and pattern discovery. We try to see patterns in the data, astronomical data, which we get from observations. So random variable, a random variable is a measurable quantity whose value depends on observational outcomes. For example, the basic definition, basic example which we use is if you are tossing a coin, it's a random experiment. Whether you get a heads or a tail, you wouldn't know a prior, but when we get it, getting a head is a random variable, getting a tail is a random variable. Similarly, in the context of astronomy, we are measuring stellar magnitudes. Yeah, so the measure of stellar magnitudes, it's a random variable. Suppose we are looking at galaxy redshifts, this is random variable, photon counts coming from a source, or the pulsar timing residues, and exoplanet transit depths. These are all examples of what a random variable is. And the important concepts which we get to know are the probability density functions, cumulative distribution functions, expectation value, variance, and uncertainty in that. So probability density function is essentially a function which describes how the data is distributed. What is the probability of finding a certain type? For example, if we are measuring the sizes of galaxies, these could be a continuous function, while if you are counting the number of stars in a star cluster, it can be discrete. So the data which you get can be discrete or continuous, and there are various probability density functions which describe the chance, the likelihood of finding a certain thing. For example, we have the Gaussian distribution, which is also known as the normal distribution, and this is given by this function as given in the function described here. 1 by root of 2 pi sigma square, exponent x minus mu by whole square by 2 sigma square, where mu is the mean and sigma stands for the standard deviations. So the application of this are finding the instrumental noise, astrometric uncertainties, spectral fitting, and so on. A lot of astronomy data. In fact, a lot of distributions which we see in nature, they follow the Gaussian or the normal distribution. And this is the beautiful bell curve which describes this function. And you will see different regions where, like, for example, at 68%, it shows all the points in the data which are below the 68% of data points are lying below this line here. And the one which ends at green, it shows all the data points, observations which are finding below 95% and so on. So this is a typical graph which we get where the mu, the average mean, is 0 and standard deviation is 1. So if you have a different mean, then the peak shifts to a different point, and standard deviation, if you vary, it will become broader or thinner depending on what the value is. Most natural phenomena you see appear to follow this normal distribution, and it's basically because of they appear to follow the central limit theorem. The central limit theorem is also in the foundation of statistics, and basically central limit theorem says that whatever the underlying distribution may be, if you pick up many samples and if you find the means of these samples, those means will again follow a Gaussian distribution, right? So that's somehow how it follows. But there are other distributions like uniform or Poisson distribution and so on. And Poisson distribution, the curve, this is the function which describes it, where this lambda is both the variance and the mean. Mean and variance are the same in Poisson distribution. And this is the curve which describes the Poisson distribution. You'll see that this distribution is quite different from the Gaussian one. In the Gaussian distribution, your mean, median, and mode are the same, right? While it's not so in Poisson distributions and so on. So Poisson distribution is used when counting discrete events. For example, the photon arrivals from a source, gamma ray detections, or cosmic ray counts, right? The number of data points are not much, they're very few. That's why it violates the Gaussian assumption. And this is the function it follows. So point estimation goals the goal is essentially to estimate the unknown physical parameters from the observed data. And the most common estimators which we use are the sample mean, sample variance, regression coefficients. And we we would prefer, we desire that these estimators are unbiased, they are consistent, and it's efficient, their efficiency will be high, and the variance should be minimum. Right? These are the ones which we require. And another thing which we use very often in statistics is the least square regression. So these yi's are the observations. Suppose we have set of xi's, yi's, and we expect there is a function which describes this data. And f of xi, the function f gives you the function. So we try to find a function where the deviations of the observed from the calculated from the function, the squares of those is minimized. Yeah, so this is the function. We minimize the squares of the deviations of this, and the function can be a linear function, it can be an exponential one or logarithmic one. It depends on the kind of data we have. So it's very often good to plot the data and see the trend, and you fit a function. The one which is shown in this image here is a linear function, a straight line which is trying to fit to the blue data points. And we are trying to find a function where the deviations, squares of the deviations are minimized. And the applications of these are many. You probably have seen the Hubble's famous diagram. He looked at distant galaxies, saw its redshifts, and set a straight line. And to obtain the Hubble parameter, you try to find the regression line which fits it. And from the slope of it, we can find out the Hubble constant, right? So its applications are many. It's used in orbit fitting for planets, exoplanets, spectral fitting, estimating cosmological parameters and so on. And the advantage is it's simple and it's fast, it's very convenient. And the limitations of this is it is sensitive to outliers. So if these are outliers, then they can very strongly change the fit of the line. So we have to make an estimate of the outliers, maybe remove them before fitting the function and then use it. So these are the outliers create a problem when you are splitting this. So maximum likely estimates is where you try to find those functions where which gives you the most likelihood, the probability of finding the functions which are most likelihood one. So your likelihood function is given by this, where f xi bar theta gives the if theta has occurred, then what is the likelihood that this function has at xi the function has a certain value. And similarly, we have these log likelihood functions. So these maximal likelihood estimates chooses parameters maximizing the likelihood. And the advantages are they are statistically very efficient, they are widely applicable, and they stick to the natural confidence intervals. And the applications are there in a variety of things, then CMBR, cosmology, exoplanet transit modeling, and so on and so forth. Another aspect which is used in statistical analysis in astronomy is the hypothesis testing. So basically, one typical question which we ask is the detection which we receive, is it a signal or is it noise? Is the signal real? And suppose you have two different samples and we want to compare them, or if you have a single sample and you want to infer the population from this, we use the hypothesis. So the framework is we set the null hypothesis. So for example, suppose we have two different samples. The null hypothesis says that the two samples are the same, right? You don't give a bias to one or the other, right? While alternative hypothesis is where you say the sample A has a higher mean or variance than the sample 2 has, and so on. So when we do certain examples, we'll get to understand this better. And the possible outcomes are we may have errors, which are usually classified in these two types, type 1 and type 2 errors. Type 1 errors are the false positives. The test shows a certain thing is of a certain type, but it may not be. That's called the false positive. While the false negative is the test shows that it doesn't belong to a certain category, while it actually does. These kind of things we were very familiar with when we were living through the COVID times, when people were testing for COVID and we were getting false positives or false negatives, where people were being shown as they were COVID affected while they were not. This is an example of a false positive. While false negative is they are found, a patient would be who has COVID, the test shows they are not, and these are the false negatives, right? This was the one which we had seen in the with the test which we saw in COVID. And similarly, these apply to in astronomy, where we try to test certain astronomical data, and we think that observations which we get are agreeing with a certain category, but they are not. So that gives you the false positive win. So the important quantities are the levels of significance. We accept or reject the hypothesis at a level of significance. And this is done by using the p-value. And for example, whenever you are dealing with data, you can't for 100% say this is what it is. So what you infer from data statistically is the level of significance. At what level of significance are you accepting a certain thing to be true or false? So I've listed out just a few of the common statistical tests which we very often use: the chi-square test, which is the goodness of fit; Kolmogorov-Smirnov test, which is a typical use for distribution comparisons; Anderson-Darling's tail-sensitive comparison; likelihood ratio tests, which are the nested models; and the t-test, right? So each one, it's very important to understand the underlying data to know which kind of tests we have to use, whether it's discrete data or continuous data, whether it is the sample size is small or large, and so on. And accordingly, we have different tests for different ones. So coming to the Bayesian statistics, this Bayes theorem is a new paradigm of doing and understanding statistics. The p theta bar x, this says what is the probability that event theta occurs if x has already occurred, right? For example, if I'm tossing, say, two dice, and I'm looking at the sum of the two numbers, so I can get from when I'm throwing two dice, the minimum I can get is 2, and the maximum I can get is 6 plus 6, which is 12. So between 2 and 6, we can get a variety of possibilities, and getting, say, a sum as 8, getting a sum of 5, they all have certain probabilities. So that will give you what is the probability. But once I know that I've done the experiment, I know that an even number has occurred, then what is the probability that it is 8, right? So that is called conditional probability. And for example, if I'm measuring the sizes of galaxies, I know it's an elliptical galaxy, then it puts some restrictions on what's the probability that its mass is certain, right? So this is called conditional probability, and the Bayes theorem gives you what is the probability of getting theta value theta if we know that X, a priori that X has happened. So once you know the a priori probability, then the likelihood of a certain thing happening changes, and it affects the posterior distribution. So advantages are, which includes a prior information. If you are calculating probabilities without having prior information, you get a different estimates of or chance of a certain thing occurring. But if you have prior information, if you have certain insight into the system, then your prior information changes. It produces full parameter distributions, and it is excellent for complex models, right? So applications, the planet orbital technology, and we have this Markov chain the simulation, and the purpose is to explore complicated process distribution, and we do simulations. They are algorithms, tasting, sampling method, Hamilton's Monte Carlo. There are a variety of algorithms which are used, and the outputs we get are the prosperity distribution, credible intervals, parameter corrections, and so on. So Markov chain and Monte Carlos are very often used for parameter estimations and so on. They are used a lot in cosmological um, uh, cosmology, where when you are looking at different models, different parameters, you can do simulations to make estimates or the derived parameters for this model. And the practical astronomy tools, MC, PyMC, and STAN. Bootstrapping resampling is again very interesting and important. It is used often to generate synthetic data by sampling with replacement. If the data sets are very small and we are unable to make statistical inferences, then bootstrapping is used to do that. And you construct authentic data from the data which we have. And these are uses are to estimate uncertainties, to build confidence intervals, and evaluate and model stability. The advantages are the assumptions are few in this, and it works for complicated statistics. The limitations are the computationally intensive and can fail for if the data is correlated, then you can have they can fail. Then okay, so we have been looking at the non-parametric methods, parametric methods. Now coming to the non-parametric ones. These are useful when when the underlying distribution is unknown. And the examples are the median statistics, we have the rank correlations, kernel density estimators, and so on. And these are applied when you are looking at luminosity functions, galaxy color distributions, stellar population studies, and a variety of different astronomical things. Another thing which we use a lot, we have been using a lot in these days is clustering and classification. So these statistical techniques can be used for clustering. We have the k-means clustering, hierarchical clustering, support vector machines, random forests, and so on. So for example, if you have observations from a certain region of the sky for a certain RA deck region, and we are getting stars from this group, if you want to determine or find clusters in it, whether you try to see by giving certain parameters, find clusters grouping in this set of stars, and to determine whether stars belong to this cluster or not. These clustering and classification algorithms come very handy, and especially when the data sets are very large. So if you look at Gaia data sets and so on, that the tremendous amount of data available in the 5 parameter space, and we can use these clustering methods to find out clusters within this set and so on. And the applications are then in a variety of things in galaxy morphologies and variable star classifications, membership determinations of star clusters, and transient detections. Then we have the time series analysis, uh, where we can detect the periodicity, identify transient events, model the stochastic variability, and so on. The common techniques used are the Fourier transforms, wavelets, autocorrection analysis, and so on. During this course of this, we may not be able to cover all of this, but some of these you will see again and again when we are doing certain examples and so on. And the applications of time series is exoplanet transits and pulsars, AGN variability and all, where your data is taken over a certain period of time and you are trying to see patterns in it and find inferences. So the practical advice for researchers is it's very important to understand the assumptions behind every method. And see, for example, then visualizing data before modeling. Like I said, when you have for a chi-square, you are trying to fit a straight line or an exponential curve or a periodic function. You better do some data visualization. Just plot the data, just do a scatter diagram of the data and see what the trend is, and then try to set the models and do it, right? Use simulations and bootstrap for validation, avoid overfitting, and report uncertainties very carefully, right? If there are uncertainties in your inferences in your data, it's always important to keep them in mind and to report it. And responsibility is essential. We cannot be using these things as a black box. The way you use a certain test or so, we do it. Yeah. And the recommended software is Python, R, Stans, PyMC, and so on. But in this course, we'll be looking more at Python. We'll be looking majorly at NumPy, SciPy, AstroPy, and so on. And in summary, astronomy increasingly depends on advanced statistics, and classical methods remains useful but have limitations. Bayesian and computational methods are now becoming the whole statistical analysis. Non-parametric and machine learning methods are also growing rapidly, and careful statistical reasoning improves scientific reliability. And I would like to basically touch upon a few of these tests which I mentioned about. For example, chi-square test is used for categorical data when you have frequency or count data, and it is used for small samples. When n is less than 30, the sample is considered to be small, and if the number of observations is greater than 30, it's considered a normal and large sample. So small sample is when your n is less than 30. And the formula, we have seen this, observed minus expected, a square, and we have the expected frequency. And for example, chi-square test is used, say, this category data. Suppose we have a galaxy survey, and the survey predicts, we are thinking that there should be 50% of spiral galaxies and 30% ellipticals and 20 are irregular, right? But when you observe 200 galaxies, we find that there are 120 spirals, there are 50 ellipticals and 30 irregulars, right? So essentially what we are seeing that there are about 60% spirals and there are 50% ellipticals and 15% irregulars. And the chi-square test is used to determine whether the observed galaxy counts, whether they differ significantly from the theoretical expectations or not, right? So you have this expectation one, and the data if you see is categorical. Yeah, the categories spiral, ellipticals, and irregulars. And we use this to say we try to infer from this observed sample whether our underlying theory, the population which we expect it to be in certain way, is it surely there is a difference. In the 50 we are getting 60% here, and instead of 30 we are getting 25, and instead of 20 we are getting 15. But whether it's statistically significant or not is what chi-square test tells you. You calculate the p-value and get it. Smirnov, yeah, so this is used, as I also mentioned, it's for discrete data, right? Kolmogorov-Smirnov KS test is used for continuous data. Yeah, when we are comparing continuous distributions, either we are checking two different sets and we are trying to compare the data. So continuous is, suppose you are looking at, say, the sizes or the luminosities of or the masses of star. It could be any value. You don't have fixed discrete data. It can be any continuous floating point number. And when you are comparing continuous data, we use Kolmogorov-Smirnov test, while this was for discrete data. And it's checking whether the data follows a theoretical distribution, right? Or whether you compare two data sets. You have cluster 1 and cluster 2, and you are trying to check whether both are similar, statistically similar, or they are statistically different. Or from a single sample, you try to infer whether the population, that sample is a good representative of the population or not. For example, it can be applied for stellar brightness distributions, galaxy velocity distribution, exoplanet orbital period distributions, and so on. An example, suppose astronomers measure brightness values for about 500 stars in a cluster. The theory predicts that the brightness values should follow a normal distribution, right? And the KS test is used to determine whether the observed brightness distribution matches the predicted one or not. And the test compares cumulative distribution measures the maximum differences between them. Coming to t-test, t-test is used when you have means. Suppose you have two different groups, two uh, sets of observations, and we have means of these distributions, but we don't have their standard deviations. Yes, we don't have standard variance is not known. And t-test is used for small sample. So when we are comparing averages of two distributions, and we want to determine whether they are statistically different or similar. And this is the formula which we use, and we do it. Okay. So for example, astronomers compare average star temperatures in two regions of galaxy. We are looking at the inner galaxy, and the mean temperature is 6,200 Kelvin, while in the outer galaxy, the mean temperature is calculated to be uh, 5,900 degrees. Whether this difference is statistically, can we say that the star mean average temperature in the uh, inner galaxy regions of galaxy and the outer regions, whether they are statistically significant or not? This is where the t-test comes in. And I will share this document with you. And in detail, we can have look at these things again later. Okay, now coming to the matplotlib, which uh, we require to do. Here's Jupyter Notebook, and it's available on the GitHub. And this is a very basic introduction to matplotlib. A little bit of it was, you had seen it in the previous session too. And this will show you how to create basic plots, how to customize plots, how to work with multiple plots. Suppose you want to have a mosaic of plots where you have a grid of 2 by 2 or 3 by 3 plots, and how to create bar charts, scatter plots, histograms, and pie charts, and how to add titles, labels, legends, and grids. Okay, so here is the first block where we are importing matplotlib. Import matplotlib.pyplot splt, right? And import numpy as np. And the first one is I am defining, say, I am defining x and y. X is a list of 1, 2, 3, 4, 5, and y we have some values 2, 4, 6, 8, and 10, and we want to plot this. So x is this, y is this, and we have imported matplotlib.pyplot as plt, and the command here is plt.plot xy. So when we plot it, we get this graph. Suppose I say further, I write plt.grid true, then I can put a grid in that. And suppose I want to have a title to this plot, I will uncomment this line, and the plt.title, and in inverted commas, whatever you write here, simple line plot or whatever, it comes as the title of this. And as you see here, we don't have x and y labels here. So if I use this command plt.x label, and whatever you write in invert commas, it comes out there, plt x-axis. And similarly, I have plt y label, it will give me the y label too. Okay, so it's as simple as that. You have two data sets, x and y. Note that x and y, the number of um, uh, entries in both have to be the same, otherwise it will have a problem when you plot it. So each one has 5 entries in it, and it plots it, right? So the simplest part of it is you can ignore all these things, and you have x as this, y is this, plt.plot, and show plot, and there it is, right? But if you want to make it a little more uh, interesting, and with the title and x and y axis and so on. As we proceed, you will see that plot, uh, we can plot, say in the same plot, I can also have another plt dot plot, and I plot x and y star y bracket. Sorry, say y to the power of, wait, in the next one we'll see that separately. Uh, so yeah, so we can even customize these plots further by specifying the line style. When I did not specify, when I simply had this function, I am plotting x is np.linspace, which we saw in the previous one. Linspace is a function from 0 to 10, and there are 100 entries in that, equally spaced. And y is np.sign, and we have plt.plot xy, and we can set the titles in x label and y label. X label is x, y label is sign of x, and this is what we have. But suppose I add further, if I specify, say, the line style should be dash dash. So you notice that your line style has become dotted line. If you don't specify, it takes the default one. And I can even change the line width, and I can make it say 4, and you will notice that the line width has become thicker. Okay. And further, so I can also specify um, I can also specify marker. I remove I just specify the marker and I do it, then I'm plotting it with circles here. Okay. So you can change the line style, you can change the line width, you can change the marker, you can change the color and so on. Okay, you set the title, you can set the X label, Y label, and so on. Now, suppose we want multiple plots in the same curve. We have again this X as NP linspace 0 to 10 in 100 spots, and one is via PLT NP dot sine, and the other plot is cosine, and we are setting labels as sine and cosine, and we are setting so if you plot it, you are getting both in the same one. And I can even set the grid true, and we can set a legend, plt dot legend, X label, Y label, and so on. So once you put those, then even the legend appears there. If you don't specify where the legend should be, it finds Python finds a suitable place to put it. Otherwise, you can even specify where you require it to be, on top right hand corner, or bottom right hand left hand corner, or so on. Okay. So this is how we are plotting PLT plot this and PLT plot both in the same curve. And I did not specify the color, but since there are two plots, uh, Python itself decided to find two different colors to do it. You can even specify what color you require. Then we have the scatter plot. So we are creating two sets, X as NP random 50 such points, and Y NP random rand 50, two sets of X and Y. And we are creating these points, and plt.scatter. So, for example, I and yeah, so I'm creating these two sets, and if I press X, you'll see it has created 50 random numbers, right? And I didn't specify whether it should be normally distributed or uniform. So it just random function is using. And similarly, um, it has created 50 I such thing. And then when we are using plt.scatter, it is doing a scatter plot of this, right? Similarly, for the above one, where our X and Y were these, I could have done a plt dot scatter X comma Y, and you see the scatter plot here. Okay, so plt dot scatter, plt dot plot, and we come further, and we can even have plt dot bar. Suppose you have categories, elliptical, spirals, lenticular, like A, B, C, D, and we have values. There are 5 ellipticals, 7 spirals, 3 lenticulars, and 8. These are the values for that. And when I do a plt dot bar, you can hide these things, plt.bar, it is giving you a bar plot and it is giving you ellipticals and it's showing there are 5 of them spirals, there are 7 lenticulars and so on. And further, like we had done earlier, you can put title to that. You can put X labels and Y label and so on. And then you can get a title to the one, and we have X label, Y labels, and so on and so forth. Here's an example of doing histograms. So as you would have guessed, to do a histogram, we have to do plt.hist. Now the question is whether it should be hist or whether it should be histogram. Like I specified in the previous one, if you say plt.dot and use your tab, it will show you all the drop-down menu. And to make it faster, you can say HI and press, and there you have hist and hist2d. So hist is what we require. And then you specify your data there. And so suppose I don't specify the bins data and I plot, it decides the bins size by itself. It is taking bin as from -3 to minus, yeah. It has decided the bin size on its own. You can specify the binning of data by say bin 30 or bin 20, right? This is bin 30, bin 10. So it breaks up the data into that many bins, right? Bin 10. So into 10 bins, and then it's plotting the histogram. Coming to pie chart, again, when we have category data, the sizes suppose are 45, 40, 10, and 5. And we have labels, again, ellipticals, lenticulars, spirals, and irregulars. And uh, we do plt.pie, yeah, plt.pie for the sizes. And we say labels are from this labels. And yeah, so this is just specifying the percentages. In what format should the percentages be written on top? And it is saying it should be a floating point number with 1 after the decimal place, 1.1 f, floating point number, real number. And if you do it, then it is giving you the pie chart, and it is distribution of these galaxies where the sizes are different sizes one. Okay, so it's as simple as that. And coming to, if you want, say, subplots, suppose you want multiple plots together. In the previous one, we had plots of two functions in the same graph. But suppose you want to plot the functions separately, then you use this command fig, comma axs equal to plt subplots. Yeah, the important thing is subplots, and 1, 2 specifies it should have 1 row and 2 columns. And the figure size we can specify, right? You can do it even without specifying the figure size. And without specifying the figure size. So it gives you by default certain size. And so you notice axs 0, we are plotting the sine function. So 0 specifies the 0th one, and the title for this one, right? This is the array goes from 0, 1, 2, 3, 4. So the 0th row and the 0th row, first column, 0th row. You will see where if you have 2 by 2, then we'll specify in a different way. So if you wanted the figure size to be a certain size, 10 comma 4. So it is plotting the mm, mm, the 10, its length should be 10, then its height should be 4, right? So you can vary these sizes and you can play around to see what suits you the most, and you can plot these things the way it appears to be. Okay. Now another important thing is if you want to save these figures which you want to attach it uh, to your article which you are sending for publication. So you use, say, I'm having x as 0 to 10, 100, and we have the function y which is x square, and we are plotting xy, and we want to we have the title as this, right? Whatever you have, and you want to save it. You say plt dot save fig, and whatever name you specify, myplot.png. And if you have this PLT show, it will show it on the screen, as well as it saves it saves it in your directory. So where you have kept your file, you can specify the path where you want to save. If you don't specify it, it saves it where your Jupyter notebook is, the location from which you are running your Jupyter notebook. That's where it saves it. Okay, so in summary, we have learned these basic plots, how to customize them, how to create scatter plots, how to create bar charts, histograms, pie charts, subplots, and saving figures. Then there are some exercises for you to try and do it. I will also show you, I will share with you this multiplots in Matplotlib. Part of it I have already done, but when you want to say have multiple plots of this kind, you just notice it's exactly what we were doing. See, figure, axis, PLT, subplots, and here I'm specifying 2 comma 2 instead of 1 comma 2. I'm saying 2 comma 2. That's why I'm getting 2 rows and 2 columns, right? And we specify uh, axis 0, 1, 2, 3, which one you want, right? 0, 1, 2, and 3. And for each one, we are setting the titles, we are setting, we can set legends, we can set up, and so on, and do it. So there's nothing much for you to be explained here, but you can, I will share this Jupyter notebook with you too, and you can see how you can create. For example, here I am creating subplots where I am having subplot mosaic and the figure size is so on, and I'm specifying what a-axis and here you are, right? So these are all examples of doing various plots, and right, 2 by 2 plots and and there are certain which I'll share with you. So with this, I will stop here, and Priya ma'am will take up Seaborn, and Seaborn helps you to make these plots much more elegant and beautiful. Matplotlib is much more simple. It does most of the things you like, but Seaborn, as you will notice now, helps you do it in a very beautiful way. Okay, so I'll stop with this. Are there any questions?
Ask them.
Are there any questions?
I don't see any question in the chat. Thank you, Jim. Maybe Priya can go ahead, and then later on, when she's done, we can ask general questions.
Okay. So Priya,
If there are questions, you can anyway ask afterwards also. So you can just write it down in the chat window and we'll address it later. Yeah. So hello everyone. And I'm sorry, what I will be doing is going to kind of be a little overlapping to what Sir has done. Uh, Basically because it's difficult to exclude these things, but there'll be some things which will overlap. But I hope that will help in, explaining these concepts to you in a slightly different way. Okay, so today our focus is on visualization, on the visualization of data. Basically, that means plotting, right? And we are basically going to do three things, not just two, but the two main in focus is Matplotlib and Seaborn. And then there's another one also called Plotly, which is an interactive visualization. So Plotly actually is the most fun part of these because you can interact with your visualization. And I'll show you how it is. For example, if you do a 3D plot, you can rotate it, look at it from up, down, left, right. So, it becomes much more interesting and much more fun. But let's first start off with Matplotlib and Seaborn. So Matplotlib is the simplest library which we have, and it's basically, it will give you your various kinds of visualizations, which Sir already spoke to you about. And what we basically need to see is what are the different kinds of plots. He already showed you how do you add labels, titles, legends to plots, and how do you put these things, right? So let's start off with the first, what you say, this notebook has been shared with you on the GitHub page, so it's there. And this is the usual thing. You have to import Matplotlib, Seaborn, and NumPy and Pandas. Now this I told you already yesterday, that this isn't it isn't a hardcore rule, but generally what happens is that when we plot NumPy things, right, NumPy arrays and all that, generally we do the plotting with Matplotlib. Okay, that's the simplest plotting machine that we have. And then the other one, which is called Seaborn, Seaborn has been actually built on Matplotlib. And hence, you actually have, again, Pandas has been built on NumPys. So what happens is the basic plotting, which happens with NumPy arrays, etc., is what you will plot with Matplotlib. But then the more specialized ones, which you may do, that is with, for example, with Pandas, that you would actually generally plot it with Seaborn. Though it isn't a hard and fast rule, you can also use Seaborn to plot arrays, but generally this is the thing which is normally done. Okay, so there are some simulated data which you can see over here. This is a simulated data of stellar mass versus luminosity. This is for scatter plots. There's one about variable stars, because variable stars is also a very important field in astronomy nowadays, because earlier in astronomy, people were basically studying the stars, static sources, but now we know that most sources are transient. That means they change with time. And therefore, what we are now plotting is variability curves. We want to see how the brightness of a source varies with time. And this is very important, for example, when you're studying exoplanets. In exoplanets, supposing you have a star, you have a planet going around it, you will basically have a change in brightness of the star because of the exoplanet going around it, right? And that is again what we call light curve analysis. So if you are analyzing Kepler data or test data, it would essentially be light curve analysis. Not only that, you could also be studying some variable stars, right? You could be studying Cephids or Ugly Ray, various kind of variable stars. And again, when you're doing variable stars, again, you would be doing what is called light curve analysis. And therefore, what happens is light curve analysis is a very important this thing. You could also be studying distribution of galaxy redshifts, which is being built over here. And there's one for exoplanet properties, okay, where we are doing this. So these are just generating different data sets. You can have a look at the different data sets. If you want, we have, okay, 1 minute. I don't know why it wants to do this. Okay, so what you can see is here we have our various data sets which we have developed. This is for the number of stars and stellar luminosities and various things. Okay, so first of all, let us understand what is the basics of Matplotlib. Okay, so in Matplotlib, every plot resides within what is called a figure. Okay, a figure is like the overall window, okay, where your visualization takes place. Inside the figure, you create one or more axes, and the axis is the actual plotting area where your data points will this thing. It's a little important to understand it. So, for example, when you want to do subplots. What are subplots? Subplots are, for example, not one plot. Say you have 2 by 2 plots, 4 plots, right? So that's when you create a structure called subplots. So subplots means the plotting area has been divided into substructures, right? So for example, you have two columns and you have 3 rows of plots, right? So accordingly, you may want to build this thing. So you could have a figure and you say you have subplots. And in that way, we'll talk a little bit more about this a little later, but you can actually have your subplots and put your plots like that. Okay. Sir already spoke about this, but we'll just have a look at this. For example, if you want to plot your simulated star masses versus luminosities, okay, that's what we just did 2 minutes ago when we tried to this thing. We tried to 1 minute is taking a little while, so we'll. I'll just see why is it taking time. Yeah. So you all already spoke about this with sir. You could actually have a scatter plot, you could have a bar plot. So you have to specify the kind of plot you want, right? And based on that kind of plot you want, you will this thing. Okay. I'm just interrupting this one so that we move on to our piece. Yeah. So here what have we done? We have plotted mass versus luminosity, right? Now, obviously, you can see that this is, if you were to convert this to a log scale, then you will get a linear plot. But while it is not a log scale, you have it like this, right? So what happens is you put your scatter plot, you say star masses versus star luminosities, you put your labels, etc., and you plot your show. But accordingly, you can also make various variations in your plot and change it as you want, right? A scatter plot, for example, another example is of period versus radius. This is for exoplanets. So here we have a list of periods for exoplanets. This is in the form of a data frame and the radius. And what we are plotting is we are plotting period versus radius. So what happens is often you can see that your plot needn't be suggestive of a trend, right? Like here, when you look at this plot, will you actually say that the planet radius is kind of related to orbit period or no, right? So that's an important question to ask. And if in case you do have a relationship, then picture speaks more than 100 words. Your plot has to convey that. But for example, if you are not exactly seeing a trend of that kind, then your plot will display it. And using the various statistical tools which Sir spoke to you about, you can actually assess whether one thing is your plot and the other thing is the statistical tool, which will actually tell you whether there is a correlation or there isn't a correlation between X and Y. Right? And if you use the correct statistical tools, you will actually get a number to describe how well is it correlated or not correlated. So what you do is when you want to convey an idea, you have to do it with both ways. You will do it with your plots as well as with your stats, right? Because the stats will give you numbers while your plots will give you a visual display of what you thought it was, right? So for this works a lot, for example, with line plots. If you are fitting data, how would you do it, right? Now here we are again doing it. This is a simulated data where we are actually seeing a simulated light curve, okay? What is a light curve? This is the variation of brightness of a source with time. So the y-axis has brightness and the x-axis has time. And you are seeing a fit like this. Now you can see that this thing is showing you a trend, but it is not a very what do you say, it is it's not a it's not a textbook kind of a trend. And that's what actually happens with real data, in the sense if you are expecting a pure sinusoidal curve, that's not what you will get with your data. With the realistic curves, with the realistic data, what you get is generally something like this, which is something in between. It is what you say, suggesting a sinusoidal kind of trend, but there are variations. Sir has already showed you the histograms. So these are the histograms. And I'm just going to run through this because you've already been shown this. And you have already seen these. And what you can play around with is, how do you play around with the labels, the titles, the legends, the color, right? You can, for each of these plots, you can change the color, you can change the line style if it's a line, you can change the marker, the points which you have. If you want a sphere or a triangle or whatever you want, you can change it. The size and the alpha. Alpha is the transparency. So for example, in a plot, you have two sets of points, and when they are overlaid, one will cover the other one. So instead, you could have something called transparency, so that if two points kind of overlap each other, you'll be able to see both, right? So you will adjust the transparency so that you can see both the points. Okay. For example, typically this one, you may put a transparency, for example, for these points, so that the 2 points look, they show. Okay. So yeah, here you have this thing, and here you can add the transparency. Okay. Now I will start with Seaborn, because that's what I was basically wanting to do. Like I told you, Seaborn is, I think I'll open another notebook, which I prepared specifically for this one. I will upload it, one sec. Yeah, so that's Seaborn. Okay. So that's my Seaborn tutorial. So like I told you earlier, that Seaborn is basically, you'll be using pandas data frames to do your Seaborn plotting. And yeah, so we are going to see some very simple examples in this. And you'll pip install your normal stuff. This has been commented because I think it's already installed. Right. So here, first of all, we are going to create a synthetic astronomy catalog. Okay. Here, this is something which is similar to Gaia. You have RA, deck, you have the distance. You have the proper motion in RA, proper motion in deck, age in million years, disk fraction. Okay. So we are doing this to basically generate our data set, which we are going to plot with. So here is our data set, which we've done. It's called make group, and you have all these parameters over here, which is the group. You have, these are different clusters, which have an RA, deck, a distance, a parallax. This is the proper motion in RA, proper motion in deck, the age, mass, etc. Right? So this is very similar to Gaia kind of data. And we want to, first of all, plot the sky distribution. So you see that these are 3 young stellar groups, right? And for these young stellar groups, I am plotting it in terms of RA and deck. Now note the thing over here. How do we actually plot it? Now there are various hues and groups in Python, where Python will decide how to organize your data. Like an important thing when you're making plots for papers, for publication papers, always be careful that often the papers get published in black and white. Okay. So what happens is, when you're making a plot like this one, I have cluster ABC, right? You can see, you'll say, oh, I've put it in 3 different colors. That's green, orange, and blue, right? But in case, you have to kind of ensure that in case your user uses it in black and white, he or she will still be able to differentiate. And therefore, be careful when you're plotting. For example, you see here, this is C, which is in squares. This one is in terms of crosses, and this one's in terms of blue, which is circle. So therefore, even if this plot were to be plotted in black and white, I will still be able to differentiate between A, B, C, because you have squares, circles, and crosses. These are little things which you need to remember when you're plotting, because often the user who will be using your paper, printing it out, you yourself may not have a color printer, and hence you need to ensure that these are in different things. So you have to doubly do it in your things. One, in terms of color, and two, here you've changed the marker type. So the marker is different for all three of them to ensure that this problem doesn't happen. Here, if we are doing a proper motion diagram, we are seeing how are these three clusters distributed in proper motion space, right? Now you can see again the same logic which I told you, that members of the green cluster, C, if you want to put diskless or disk, you may actually put it, a disk is the one with square and diskless if it is circle. Again, you see in this we have, and okay, this one has not done that job. Here we do have the same circles. So this is not a good plot in that sense. Ideally speaking, if you were plotting it, you should have done it in some way. But the problem is because you have circles and crosses, how do you differentiate between three of them? So you need to think about how do you do it. Maybe you put them inside squares and circles and triangles or something like that. So you've got to think about how do you put it so that it's color proof also, right? If you want to plot a CMD, a color magnitude diagram, you can see how well this color magnitude diagram has come. Again, here we have this problem about colors. So be careful about the color thing, which I told you about. Other interesting plots which are done are called histograms, right? So there are two, you have, these are histograms for the three clusters which are there. They are three different distances, but obviously their distances overlap. So you have the distance put over here, and then you have what is called a KDE, which is a kernel density estimator. Okay, so the kernel density estimator is put over here, which is these ones, the lines which you can see. Did you talk about box and violin plots?
No.
Okay, yeah.
You showed last time.
Okay, yeah, last time I did show you all box and violin plots. Like we spoke about it last time, these are very, very important plots in plotting because it very well conveys the data, right? So for example, your median value is coming with the line. This is your Q1 and Q3 values, right? And then you take it 1.5 times here, 1.5 times here, so that you can see the outliers, right? You can see the spread. And this is very important to actually demonstrate data, right? It's a very good kind of a plot to have and something you should actually get used to using. Here, for example, these are violin plots. We spoke about this last time also. It's like a box plot, but here what you see is this one is giving you the actual distribution of the mass, right? So you can actually see the distribution coming like this, okay? Which is also a very useful way of plotting data, right? I don't know whether we spoke about pair plots last time, but pair plots are also very important. Typically, when you have catalog data, let's say you have 5 columns of data, right? Now you don't know how are these things related to each other. For example, here your variables are distance, proper motion RA, proper motion dec, absolute G, BP minus RP. So what you see actually in this thing is that these things are actually not related. So when you plot it, you will not get a relationship between them, right? So what a pair plot does is it plots 1 versus 1, that is this, 1 versus 2, 1 versus 3, 1 versus 4. So it plots all of them. When you do this in, so this is basically looking for correlations between all your corresponding columns, right? So in your column data, you're looking for, is 1 related to 2, 1 related to 3, 1 related to 4, which of them are related? So you do pair plots for that. And the diagonal ones just give you the distributions, okay? For each of these, with each of the parameters. So this is the distribution for proper motion RA, here's the distribution for proper motion dec. This is the distribution for BP minus RB. This is the distribution for absolute G. So the diagonal gives you the distribution, and the other components, in principle, this is symmetric matrix, right? You'll have the same thing coming over here. That's why we're not plotting it. So you can actually see how is what related to. Okay. Another important thing is what is called a heat map. A heat map also, I think Sir spoke to you about Spearman correlation. Did you talk about Spearman correlation? So basically, again, supposing I have all these columns, these are my columns, distance, parallax, proper motion RA, proper motion dec, these values. I have this plotted in X as well as in Y, right? So obviously this one is distance versus distance. So you see the correlation is 1, because it's the same thing. But if I'm taking distance versus parallax, I'm getting this, because approximately 1 upon parallax is distance. So you're getting this kind of a correlation. And you're looking for these other values also, depending upon what are the correlations. So if you have catalog data, right, tabular data, it's often very interesting or important to actually plot these kind of things. One is a pair plot, right? Or for example, this thing which is called a heat map. A heat map, the correlation is plotted over here. So depending upon the kind of correlation you have, the positive one, you could have a positive correlation or a negative correlation. So you see all the positive correlations are shades of red, all the negative ones are shades of blue. So what you do is you can actually plot this to see what is related to what. Okay, so these are simple plots which you do when you do, remember what I was talking about last time, that is when you're trying to do what is called exploratory data analysis, when you have a data set and you want to try to explore and see what are the correlations between the different columns, etc., right? So you may actually do this kind of a plot, a heat plot. Then the standard plot which you also do is what is called a regression plot. What is a regression plot? I have plotted A versus B and I'm trying to fit it, right? So Sir spoke to you about least square fit. You may do a least square fit in a linear plot, or you may do various other kinds of ways of fitting your regression data depending upon what is it. You may also do what is called a facet grid, which is I am here plotting the color magnitude diagrams by the group, right? So I have different groups for A, B, and C, and I'm hence doing 3 plots which are giving me the 3 plots for A, B, and C, right? So I can take it like this. There was also, if you remember in the beginning data set, there was what was called disk fraction for all these stars. So let's say we have some disk fraction for each of these clusters. So I'm actually doing the disk fraction by the group on cluster A, cluster B, and association C. Okay. So I spoke to you this about saving figures, and you save them. You can save it in whatever format you want, PMG, PS, PDF, whatever. Very simple to do it. Okay. There are some exercises over here, which I've put over here, and I would urge you to try doing these exercises and come back to us if you have any doubts. Now, the next thing which I want to do is something which will help you actually work on your own. Okay, these were basics which we were explaining, which are important for you to understand so that you do your stuff. But now what we basically want to do is to help you to get independent. How can you do independent? So for example, if you're working on Matplotlib, I would urge you to look for what is called a Matplotlib gallery examples, right? So for example, if you go on to a Matplotlib gallery here, right? Let's say you are already doing your work, right? And you already have an idea that, for example, you want, say, a stacked bar graph, right? Supposing I am doing it for males and females, I have data for males and females, and I have various parameters of theirs, okay? Maybe their ages, maybe their salaries, maybe whatever it is, right? Yeah, so this is a male-female example, and I have various factors, maybe their ages, their salaries, their number of degrees, whatever it is, right? So this is what is called a stacked bar graph. So I want to use this to make a graph like this, right? So what I would urge you all to do is you should be very comfortable using these galleries, okay? Matplotlib, I will after this show you the Seaborn gallery. So if you want, for example, a horizontal bar chart, okay? Then here you can click on this, click on horizontal bar chart, and here you can see this is the code. This is the code for exactly this bar chart, okay? So if you want to draw a bar chart like this is the code for it. You can freely copy this code, click it from here, you can copy it and use this onto your notebook, right? Now, if you've understood the syntax, for example, here you see, these are the names of your groups, Tom, Dick, Harry, Slim, Jim, right? So what you do is maybe you have, like what Sir showed you was elliptical, spirals, lenticulars, whatever is your, whatever is your parameter for which you're drawing the histograms, you will replace this stuff by that, right? Similarly, the numbers, whatever the numbers are, here, where do we have our numbers? You have, this is your thing. If you see, this performance is actually generated using random numbers. So we have 3 plus 10 into this. I hope you noticed that when Sir showed you random numbers get generated between 0 and 1, right? So supposing now I want to generate random numbers between 0 and 10. I will multiply it by 10 so that now my random numbers are generated between 0 and 10. So therefore here you see the performance, the base is 3 plus 10 times random numbers. How many are the random numbers? The length of people. How many people do I have? 1, 2, 3, 4, 5. So I have 5 people. Length of this people thing is going to be 5. So that means my random numbers, this is my random number seed, which is 5, okay? And I'm taking 10 into that. So you can see my values are 3 plus 10 into 10 ranging from 0 to 1. So typically my numbers are 3 plus 10, from 0 to 3 plus 10. That means 0 to 13. So here you see it's there till 14. So what happens is my performance here I'm generating as a random number between 3 plus a number between 0 and 10, right? So I'm getting these different numbers, and this is how I'm going to make a horizontal plot, right? So you may want to, you already saw how to do a vertical histogram plot. How do you do a horizontal histogram plot? So what you see is you have here, you have your people, you have your performance. We've added some amount of error. And here, look at the code. You get bar H, you see? So bar H is showing you that your bars are going to be horizontal instead of it being vertical. So the default value is for it to be vertical, which you've already seen. But if you want to do it horizontal, you will just have to have bar H, right? So that shows you for histograms, right? For example, you could be stacked bars. How do you do stacked bars? You can see it over here. I have P1 is the plot bar for, this is for men, this is for women. And when I'm plotting it, what do? I'm going to plot it as P1 is men, P2 is women. So you can see that when I plot it, I am plotting bar, this is men, and then P2 is plot bar women. So they get stacked up one on the other, right? On the other hand, if I want them to be beside each other, okay? Here I have men and women but placed beside each other. How do I do it in that case? In that case, what do? I am going to plot, this is my code, which you can see over here. Here I have the same values. I have women and I have men. But here I have rectangle 1 is this, rectangle 2 is the women one. And when I'm plotting it, I am plotting it as, you put it as subplots, and I say rects 1, rects 2. These are my axes. And then I say, when I plot it with rects for rect 1 and rect 2, and it places it like this. So I auto label it like this. So here you're seeing very simply, how do you differentiate if your box plots are stacked one on the other, or they are put beside each other, or they are put horizontal, right? Similarly, you may also look at other kind of plots. Let us look at some more interesting plots. For example, let's see something, we can come to something down over here. Often an interesting plot is, for example, if you want to do contours, right? Contours are interesting plots. For example, I want to do a contour like this, right? I want to do a contour like this. So let's see, how do I plot a contour of this kind, right? So the idea is you basically go to the gallery, right? And from the gallery, choose the kind of plot you want, right? The gallery may also help you in getting ideas as to what kind of plots should you use. Like I showed you, right? For histogram, you can do stacked plots, you can do beside each other, you can do horizontal. Similarly, when you're doing contour plots, you may see this contour plot and you may say, oh, this is a nice kind of contour plot. You may also like some other kind of contour plots, which you may also observe and see it, right? This could be, for example, a contour plot of irregularly spaced data. So let's say you have data which is irregularly spaced. You see this data. And now for this data, I'm actually plotting contours. So you can see it's overlaid of two plots. One is a scatter plot and one is a contour plot, right? So how do I plot these things like this? The important thing that you need to learn in this class is how to read code like this. Why? Because we have not done that, but if you, for example, many of you may, for example, if you use ChatGPT, right, to make a certain plot of yours, right? Let's say you're not seeing this from Gallery, but you're seeing this from ChatGPT. So ChatGPT has generated a plot for you, right? Now, often what may happen is that it may do it, but it may not do exactly what you want. You may want a slight variation in the thing that ChatGPT plots, right? So there's nothing wrong if you're using a ChatGPT plot, but the problem is that you have to understand the code so that, for example, this is the code. Simple example, I don't want blue, I want another color. So how would you find the blue color? You look into the code, you can see here, the code is coming from what is called the color map RDBUR, right? So you have to then look for other color maps, okay, in Matplotlib. You see color maps in Matplotlib. These are different color maps in Matplotlib, right? You see these are the different color maps, okay? So we'll go back to my example. I hope you can see that. Let's see in our, oh yeah, sorry, this is the example. Here you can see in this example, it has used the color map RDBU, okay, RDBU underscore R. So you can see this is one RDBU, right? RDBU, yeah. So what happens is these are the sequential color maps. There's a second sequential color map, which are these, which are these, which are these. So what you need to do is basically, like I said, when you read this code, you need to see, oh, this is the color map. So if I want to change the color map, where will I change the color map? You see, here's another color map. You may also, for example, instead of 2 by 2, you may want 3, right? Then where do you change that, right? So how will you change that? You can see over here that when we've described it, we've said figure, we've said axis 1, axis 2. Number of rows is 2. You may now want your subplots. You see, these are the subplots, 1 and 2, 2 rows. You may want to, for example, make it 3 or 4. So what you basically need to do is to understand how to read this code so that you can change it to your liking. So somebody yesterday or last time class asked, what about using AI for plotting? There's absolutely no problem in using AI for plotting. The only problem is that AI may not exactly make the plot you want. You may want to change it. But to change it, you have to understand this code. Okay. When this AI generates a code like this, you have to understand what does it mean so that you can then tailor make it for your liking. You understand? Because often on the prompt, what you may tell AI to generate, it may not exactly generate the thing you want, right? So the correct way I would suggest to work is that use AI, no problem. You can use ChatGPT, you can use Gemini AI, you may use GitHub Copilot, you may use whatever you want. But you have to understand the code that it generates, okay? So that when you read the code, right, you should be able to understand what does this mean? X is equal to NP random uniform minus 2 to 2 endpoints. So you've got to understand that this is the range in which you're taking it and this is the number of points. Endpoints is already described as 200. So now if I want to make this 2000, I should know where should I edit it, where should I add the thing I require to increase the number of points, right? Similarly over here, when you're saying xi is linspace whatever or yi is linspace, you need to accordingly see it and do it. So the correct way I would suggest to work is you can use the gallery, you can use AI, but you have to understand the code which it writes so that you can accordingly adjust the code to your liking. Okay. So I will now go on to, instead of Matplotlib, I will go on to the Seaborn library, so, or the Seaborn gallery. And let us look at the Seaborn gallery. Okay. So the Seaborn gallery, if you see, here is the Seaborn gallery. And here is it. It has Seaborn, like I told you, is built on Matplotlib. So generally the plots which are made with Seaborn are far more appealing, far more beautiful than the ones which Matplotlib does, right? Matplotlib does something more basic, while Seaborn does a little bit more fancier version, right? So let us look at this one. Look at this one. Like I said, you have to look at the gallery, choose the kind of plot you want. Like I told you, often the gallery may also give you ideas as to what can you do with your plots, right? To make your plot look different, right? So you can actually see this and accordingly think of what is the plot you would like. So you can have a look at various things and accordingly this, you see, this is also violent plot, this is also violent plot. You may opt for one or the other for whatever reasons. Let us look at this plot. Okay, so here what is this plot? This is a plot of x and y, a bivariate plot with multiple elements, right? So this is, how is this created? This is created, it's a Gaussian, right? If I were to slice this, if I were to slice this along this axis, right, I would basically get a Gaussian, right? And that's what I would do, right? And you would get this Gaussian from this. And how do you generate it? You have a number n, I have a mean this, I have generated random for a multivariate normal. Normal distribution is a Gaussian distribution. This is the mean, this is the covariance, this is the n, and we've generated this. So here what you see, however I plotted it, one is a scatter plot, right? The other one is a Hist plot and a KDE plot. So here what you're doing is you're doing a combination of this to produce it, right? You can also have a look at various other plots. We were talking about bar plots. We already saw this one in Matplotlib. You can see this also in Seaborn. You see the Seaborn one is slightly fancier. You could have different, what do you say? You can have different palettes, okay? So what you would play around with is, for example, the different palettes. You can actually check it out. You can see what are the different palettes in Seaborn, right? Here you can see the Seaborn palettes. So you have various palettes which are there, okay? And hue is the component that differentiates different colors, and you can actually choose it. You can vary the hue, and you can actually take different palettes. So if you want your plot to look like this, or like this, or like this, you may actually choose. So you have a color palette. You can take this tab 10, you can take pastel, muted, bright, colorblind, deep, whatever. There are different kinds of palettes, and it's very important to actually give attention to these things, because these are the factors which make your what do you say, which make your plot looks good, right? So you need to pay attention to these different palettes, okay? And have a look over here and whatever, okay. Oh, I didn't continue this. Or did I finish? Oh, okay. I will go on to one more point before we go on to more these things. Is let me upload and I will show you the fun word which I wanted to show you. This is Plotly. Okay, Plotly is yet another plotting thing which you can use in Python. And like I told you, this does interactive plots. Okay, so you'll see what is the interaction like. So we'll say, let's say it's this thing. Okay, so now this is my interact. What is interactive? For example, the same example we are using, the ones where we have A, B, C, 3 clusters. If I bring my cursor here, you see this is already giving me stuff about my thing. Oh God, 1 minute, why did it do this? Okay, let me run this. What happened to fixture? Okay, there's no fixture. Okay. What happened to it? I don't know. Okay, let me continue with this. See, again, it's not plotting. I think something went wrong with my notebook. What is the problem? Okay, I'll look over here and we'll see Plotly gallery. Okay. So Plotly also, like exactly like I showed you in that thing, the ideal way is to work with a gallery, right? So a gallery, what happens? You will have this interactive thing, right? I'm sorry. Let me go to something else. Okay, let's go to this. This is simpler. So here, Plotly, what happens is that when you get into the thing, I don't know, the notebook was working fine yesterday, but you want to take Najam. What you'll see is that you can actually, yeah, yeah, okay, you can see over here, I can actually, supposing I have plotted this thing, right? I have plotted my histogram. But if I want to adjust it, I can actually pull it around. I can, change it. I can zoom, double click to zoom back. I can do whatever I want, right? You can see this. For example, here I have this. Yeah. You want to take over? Yeah. Yeah, okay, I'll just try to debug my notebook till then, sir will continue. I'll stop share. Yeah, I'll just clear that thing.
Yeah, so while Priya debugs her file, let me continue with to link up what I started off the presentation for statistics. And here we will see some examples. I'll share these um, hypothesis testing. And so here's a Jupyter notebook which shows you how we do chi-square test and Kolmogorov-Smirnov test. Okay, so this is an introductory one, and basically what we are doing in this will be shared on the GitHub, or I'll share it now. We are importing from SciPy import stats. Okay, the import numpy, NP, and matplotlib, PLT. These are all for plotting and further things. But to do the chi-square test and case test and so on, this is what we require from SciPy import stats, and from SciPy optimize import curve fit. Curve fit fits a curve to the data which is given to you. Okay, so SciPy is pretty rich in these things, and yeah, and here we are using PLT style use Seaborn, which Priya ma'am just specified. There are various dark grid and different ones, just for beautification. But important thing here is these are the two things which you have to see. From SciPy import stats, and from SciOptimize import curve fit. Okay. And then this is a block which tells you what the chi-square thing is. This formula you have seen it, familiar one. Observed value is expected value squared by expected values here. And we are fitting a spectral line of a Gaussian fit to some data which we generate. So basically here we are generating some synthetic data Okay. And with Gaussian noise, you have seen now how to create this random data with Gaussian. Remember, we had done np dot random dot normal brackets mean, then standard deviation, and then number of points which require. So we'll be using that to create this. So in NumPy, you can create random data points as Gaussian distribution, in uniform distribution, in there are various ones which are stored there. So we are doing that. So NP random seed, you should keep changing the seed number, otherwise it will create the same number. So as you change the random seed, then when you run it again with another one, it creates another set of random numbers. Otherwise, if you run with the same seed, you will generate the same random numbers again and again. So true amplitude is 10, true mean is 0, and sigma is 2. So we are defining this Gaussian distribution, yeah, with x, this is the mean, these are the values, and amplitude given here, and the mean and the sigma, okay. And we are creating this, and we are creating noise, some random noise to it. Yeah, this is synthetic data. If you take the actual data, which we will do if we get time for that, we won't have to do that. You'll take the actual one and do it. But here I'm creating some flux, some observed flux with some noise in it. Noise is created here. It's the noise which we are using is random noise with mean 0 and standard deviation 0.8. And the size, the number of points which we are doing are the number of points which are there in this x which we have created here, from -10 to 10, 50. So len x will give you that size, and we are defining this size to be that. Okay. So we are creating that, and we are plotting it here. And this is what we have here. And we are plotting plot error bars for the x observed flux, y errors are this, where, right? And we are formatting what the point should be like, and the size, and the labels, and so on. This we have already seen. Setting x label, y label, title, and so on. And here is what we have simulated spectral data line. Then we do the curve fit. Yeah, we are using this curve fit, which we have imported, and we are fitting a Gaussian to the data with the errors which are specified here, and we are getting the best fit, and the best fit parameters are given here. Okay, the mean is this, and the error in that, sigma and error, and we compute the chi-square and reduce chi-square by uh, in this block. And you notice it is np dot sum observed minus the best fit by errors whole square. Yeah, exactly the function which we have defined here. And we are computing the ones, and we are seeing that the degrees of freedom for chi-squared, we have 46.4 degrees of 47, and the reduced chi-square is 0.9. And with this, we interpret that chi-square value is 1.16, it is very close to 1. And this indicates that the Gaussian model fits the observed data well. And the small deviations is due to the added noise. Okay. So, right. So visually we can fit this data, and you can see that. I'll share this file with you and show you. And similarly, we have the Kolmogorov-Smirnov test here. And you'll see that again, we are creating two clusters, cluster A and cluster B, with certain number of samples and so on, with some noise, right? We have three clusters with means, and we are using this. We will notice here. I'll have to run this all over. Yeah, now we won't get. Yes, we are plotting this, and we are performing the case test over these two tests. And this is the line which shows that from stats, we are doing the KS test. KS test is the function, the KS test, and we have cluster A, and we are checking whether cluster A has a uniform distribution, right? So this is the example where you know that the population has a uniform, we are assuming that it has a uniform distribution. You can test it with Gaussian or uniform or whichever. So we are, in this case, I am testing the generated cluster A masses, which I have done, and checking whether it agrees with the uniform distribution. And uh, and then we accept or reject the null hypothesis depending on whether the value, the p-value is greater than 0.01 or less. So it p-value is 0.01 while the ks value is 0.1. So we fail to reject the null hypothesis, right? That means we accept the null hypothesis and say that the cluster A agrees with the normal distribution. In the other example which we have here, we are doing case tests for the two different groups which we are doing, and you'll notice that we have these are all the plots, and you will notice that we are doing, these are basically the yeah so yeah so again we are using ks here ks 2 sample, right? Ks underscore 2 sample is a function where when we are doing, we are comparing the two clusters. Okay, right? This is an example where you are using ks2 sample with cluster 1 and cluster C, cluster A and cluster B. And this one which we discussed first is where we are doing this ks test, where you are testing cluster A with the whether it's has a uniform distribution or not, right? So the important thing here is in stats we have ks underscore 2 sample, right? Ks stats under 2 sample, where when we compare two different clusters, and while ks test is done when you are testing one single sample you have and you are testing it with the populations, right? And other things here are we are plotting those, and the uh, things which Priya has discussed earlier. We are plotting these things and doing it. So this is the one which I'll share with you, and also I will share with you another file where we have this hypothesis testing, um, where we generate some uh, sample data, and here we are importing SciPy ODR, from SciPy ODR import ODR model 1 and real data, and SciPy statistics import linear regression, right? So you can do linear regression by basically importing from SciPy this, right? And just by using this, you can do a linear regression to the data which you have. So this is again a file which I'll share with you. In the first set, we are creating two uh, clusters with we simulate metallic measurements for two clusters, and then we apply these tests to uh, mm, check the students t-test, right? This is for students t-test, and right, and this is for two sample t-tests. So I'll share with this, and you can run it and see. And basically you see that regression analysis, and you can fit the regression and so on very well, and you can get all error relation and so on. Okay. Similarly with this ODR regression models, we can fit certain regression curves and get the parameters for the values. Yeah, it's fine. Yeah. Okay. So I'll stop with this, and Priya ma'am will take over.
I've debugged that file. There was some problem with it, but we just have 8 minutes more, and I'll show that fast to you. But let's have a look at it. So I'm screen squaring, yeah. Yeah, so this is my Plotly this thing. If you remember the same notebook, it's there on GitHub. And here what we're doing is exactly generating like we did earlier. We'll generate a guy like astronomy catalog. This is exactly what I did with the earlier data set, which I showed you with Seaborn. I'm doing the same with Plotly to show you the difference, right? So here if we do this, let us see the simplest plot, which we did in that case also, was a plain sky plot, right? You remember we got this sky plot, which we did it earlier also. But now because this is being done with Plotly, you can see it's interactive. For example, I move my cursor, it's showing me the data. It's showing me what is each data point. If I want to see which is the data point, it is actually showing me the data points. If you remember, the data points look something like this. You have a source ID, group, RA-DEC, etc., etc. These are all the parameters. It shows the group. But now that it's been plotted, they are group ABC, right? But now when you move this thing, it is showing you the interactive thing. It is showing you for every point what is the value, right? So that you can see with this. If you plot the proper motion diagram, again the same way. This is ABC. Over here, what they've done is that here instead, this is kind of made diskless and disk bearing. You see is round and circle, square instead of the cross. It doesn't make a difference. But here you can see again every point. It is interactive, so every point. Supposing I want to know what is this point, why is it coming out over here like this? I can actually see what are the proper motion values, 1.534 minus 4.6. So while these ones are, with a slightly different value, this guy is slightly a bit of an outlier. So I can see the value from this, okay? So what is the interaction in the sense when I move around with it, it gives me the value of every point. So if I want to know what's the problem with this point, for example, or I see this one is such a big point, how is this the size being scaled? The size has been scaled. You can see it over here. We've scaled the symbol. It's actually getting scaled by the size is by the mass. Okay. So the more massive stars, this can be actually have done even with the Seaborn and all. You can do it. You can scale the size, but here you can see that it has been scaled such that the more massive stars have larger sizes, while the less massive ones have smaller sizes. But the interactive part is this, that you can actually move through it. So for example, I want to know which is this one, which appears, this guy looks the most massive guy. So you see this has a mass of 3.13. This one has a mass of 1.17. I can see and I can check what are the points, right? If I make a CMD, for example, with this, I did that earlier also, I can again, basically it gives me the point for every point, okay? I can also, the histogram also, I can get it like this. Here's my histogram. It's made slightly more interesting made over here, where we've actually again put a bar plot over here also for each of them. So you find the median, this guy's median value, the blue one median value is here. So you can see, now it's showing me. If you remember, I had explained this to you. The bar plot, the central point is the median point. Then the up and down is the Q1 and Q3, which are the quartiles, right? The 25% quartile and the 75% quartile. And then here you have the fences, which are 1.5 times the difference between Q1, Q3 minus Q1. So this is the upper fence, this is the lower fence. So now you can see that all this has been put over here. So you can see this is the median and how is it getting distributed. Similarly for the red one, again, you have the median, the quartiles, etc. showing. And then for the green one also you have it showing, it shows up like this, right? So this proves very useful. For example, now you can see if I make a violet plot, this is a violet plot of stellar mass, okay? So all the stars have a different stellar mass, and you can see that as per the groups, we have actually made it. So we've actually done double. We've done it, if you see, we've made a scatter, and we've done the violet one. And therefore here you can see I have got the points and I've got this, and I can actually, you see I have this line, I can move this and I can see what are the values. You can see it over here. I can move this and I can get the various values, okay, for these guys. I can see this. Similarly, if I make a bar chart by disk fractions, you see all the three clusters have different disk fractions, and I can put it over here like this, okay? I can see what are the different disk fractions. In principle, you can also, you can actually even zoom into your histograms and do more things with them if you play around with it, right? So you can actually try that out also. I think you can play around with the bin size if I want to reduce the bin size, but this one has increased it, it's zoomed it. But you can check it out and actually make alterations. And now you'll see the most fun part about Plotly, which I like the most, is that you see that all these three clusters have certain X, Y, Z coordinates. I can plot it, right? And this is what I was showing you about. Here they are plotted in X, Y, Z. And now because it is in Plotly, I can actually rotate. You see, this is beautiful. I can rotate this thing. I can look at it from different angles. I can see the values if I put over here, and I can plot it as per different values and angles, right? So I can actually put it, see it from here, see it from there, get it in different points. This proves very helpful because, for example, if I want to plot it like this, you see like the original plot, you see this is a viewing angle in which I will see it like this. But if I want to view it from another way in terms of, for example, distance. For example, I'm supposing if I want to see it in terms of Z, Z is the distance from the, this thing, from the plane of the galaxy. So now I can see that in terms of the plane of the galaxy, I can actually, this is my Z, right? This is my Z, this is my Y. I can actually move it and see it in terms of X in this, right? Similarly, you can see here the proper motion. The proper motion are velocities, and therefore here's the proper motion. But this is basically 2D because it's PMRA PM deck, it's not in 3D. But in principle, if it's Gaia data, you can use it to calculate it three-dimensional velocities, and then you can again do it like this. So you can do all these things and make this nice and interesting with this thing. You can also use this to create animations, okay? So for example, here if I have an animation, you can see these are these guys, and 1 minute, oh sorry, I'll just read this thing and I have an animation, so I'm moving this with time, and you can see here I have a video which will actually move, and I can move this video and I can see the movement of these parts. These are moving very simply, nothing complicated, but in principle if you were giving it a range of positions with time, right, you can actually generate your animation, right, using this. So this part is a very simple one, but you can actually move it and do whatever you want, right, get an animation. Okay. If you want to even do a scatter plot, you can see this one. I can, again, this is the, in this one there's no rotation, you just see it and you get the points, values of the points, and you can export this to HTML very simply. So in short, there are a few exercises listed over here on interactive parallax histogram, disk bearing, this thing. You can try out these exercises and see how it works out, right? So our time is up. We will stop now, but we will just take a few questions if you all have any questions. So please write it in the chat. Yeah, okay. So in the chat, Najam, just see the questions.
When do we do fig X?
So the slides will all be there on GitHub. How can data be fitted using nonlinear regression? Najam, how can data be fitted using nonlinear regression?
You will have to define the different functions. Yeah, so we have linear. You have to define the function.
Yeah, so when you're fitting the
And try
function,
to
you will
fit the
define.
curve
Yeah.
fit. Yeah.
Basically using curve fit. Yeah. So with curve fit, you give the function. Since it's non-linear, you say whether it is second order polynomial, third order polynomial, three, whatever is the function. You have to give the model function and then you will fit it, right?
Yeah. And in the sklearn, there is this pre-processing import polynomial feature
You
where
put on
you
your
can
video.
fit the different ones.
Put on your video. Start your video. Start your video, Najam. It's not getting shared. This is not getting shared.
Yeah.
Okay, fine. Okay. We have another short question, Sergey. When do we do fig AX plot this thing? What does fig store? So fig is basically the object which you are storing in it. So you could even have fig 1, fig 2, fig 3. It is the object which you are doing, which is your space, your plotting space. Okay. So when you say fig X, it has subplots and you put it like that. So fig stores, if you have subplots or what are the details about the fig. Okay. And if you want to do another figure, you can even call it fig 2, for example. Yeah. Okay. Fine. Okay, we'll stop, Najam. If you're done. Yeah.
Yeah.
Okay then. So thank you. We'll have to stop because our time is up. And you can post your questions on Discord and we'll this thing. Which model we can use to photon sphere? I don't know. You'll have to check for that. For photon sphere, you'll have to check what are the models. There are models, standard models, which you'll have to check. Yeah, Bablu. Yeah, so which mod? I'm not sure about photon sphere. Thank you. Okay. So,
Okay.
Daniel.
Yeah, so thank you everyone for joining us this morning. Please,
Daniel,
yeah, can you hear me?
we can wind up, we can stop if you want.
Yeah, can you hear me?
Yeah, I can hear you. Sorry. Yeah.
Oh, okay, fine, that's fine, cool. Yeah, so
Yeah.
I'm saying that thank you very much for joining us this morning.
Yeah.
Thank you, Priya and Hassan, Ajam, sorry, for wonderful presentation. Please, guys, the resources are in your learning materials website. Every resources you need is there. Any further information shared by Priya will also be shared there. And please, every required material you need or resources you need for this week is in the week 3 of the GitHub repo. Please, you can explore it, go through the notebooks, and then if you have questions, you can ask in the communication channel. So we'll end it here this morning, and then we'll convene in the evening for the evening section. It's not a must that you join the evening section. The evening section is for those who were not able to make it this morning. So thank you again, and Priya and Ajam, see you in the evening. Yeah, bye.
In chat, I've put a small example of how nonlinear regression done using this curve fit. Yeah.
Maybe you can do that in the
function. It's in the chat. You can have a look.
Yeah.
Okay, good. Okay, good. Yeah, so please take a look at the chat. You can copy it before in the meeting. If anybody wants to copy. All right, guys.